Another approach in finding solutions to the 2D steady-state heat conduction problems is what we so-called using conduction shape factor. And it's a very useful approximate approach. So it's useful approach for 2D systems. There is a limitation where only two temperatures are involved. And it's a quick and straightforward calculation. It provides But what is a conduction shape factor? How we define it? If we write the heat flow equation by conduction in a general form, that is thermal conductivity, some parameters called S or shape factor, and delta T overall, that is in the system, which is equivalent to delta T divided by 1 over Ks. Here, what we have S value is what we call it conduction shape factor, and 1 over Ks is equivalent to the thermal resistance to the conduction for this 2D system. How we find S values or conduction shape factor? There's a table in the text, table 4.1, that provides the shape factor for various geometries. And I just brought a section of that table. So for each case, with these definitions, we have the schematic of that one. The second column provides the schematic of that. And the important one is these restrictions that we need to pay attention for each of case. What are the restrictions that we have? And then you can read this shape factor S in the last column. Let's go over an example here. Let's say for case 2, and just going to put an example of case 2. Example case 2 is for a horizontal isothermal cylinder of length L buried in a semi-infinite medium. Semi-infinite medium here is on one side, we are the finite, we have a temperature, but on the other side, it just goes to infinity. And it can be a very good, I would say, analogy for the buried pipeline. Okay, so let's find heat loss from a long buried pipeline that is transferring liquid, or let's say gas, in the system. So let's say we have, this is the surface ground, and somewhere down there we have a buried pipeline. This is just a cross-section of that, but the pipeline just goes deep into the system. Here we have T2. The surface has a temperature of T2, and let's assume the depth that this pipeline has buried is called Z, with the diameter of D. Now, if you look at on other sides, this medium that has been buried goes to infinity on the other side, while on the top side it is limited to this temperature T2 or to this surface. So if you want to find out what is the heat loss that's happening from this pipeline that is at temperature T2, T1. So it can carry some hot fluid or cold fluid, doesn't matter. And we want to see how much heat loss has to the ground surface. Now the known parameters here, what we know is T2, which is surface temperature or ground temperature. T1 is the pipeline temperature or the liquid in the pipeline temperature. D is the pipe diameter. And Z is the depth of pipeline. Yeah? The depth at which pipeline is buried. This pipe is buried, and let's say we know the thermal conductivity of soil, and you can read it from tables or other references. Conductivity of soil. What we are going to do, we are going to find Q, and we can, in terms of assumptions, let's assume this is steady state 2D. So the heat is getting lost from this pipeline to the ground. So it's a 2D problem. It's not really like symmetry everywhere around that we could assume 1D radial conduction. So this is steady state 2D conduction. I would say assume no convection, radiation that can happen. And then let's assume this K is constant. K is constant everywhere. With this assumption, we can use the general form that we set for the conduction, which is going to be, I'm just going to make it K of soil just to be sure or clear. This is going to be K of soil, the shape factor, and the temperature difference from the hot to the cold environment, T1 minus T2. Okay. Now for this geometry, we can find out what is the shape factor. If we come to this table, this is case 2, and it has two restrictions. If L is much greater than D for both of them, like L is the length of this pipeline, should be much greater than the diameter of that, and Z, which is the depth that has been buried. If it's less than 3 times diameter divided by 2, then we use this S factor. If it's greater than that, then we can use the other shape factor. Now, I guess let's define some parameters before writing this shape factor. Let's assume L is the length of that is 100 kilometer. D is 1 meter, and let's say it's buried in 2 meters under the ground. And let's assume K of soil is 2 watt per meter Kelvin. Now, for sure, L is much larger than D. Okay, it is 100 kilometers. And we can find S. Now, the second one, when Z is greater than 3 times diameter divided by 2, is an approximation of the first one. So I'm going to use both of them. and show the differences that they can provide. So let's say L is much greater than D. So the relationship for S is going to be 2 by L hyperbolic cosine minus 1 of 2Z divided by D. So if I read from that table, now I can replace, I can get the value of Q, which is K, 2 watt per meter Kelvin. And for this S is going to be 2 pi times 100 times 10 to the power of 3. This is length in terms of meter. Sine hyperbolic minus 1. 2Z is 2, so it's going to be 4 divided by 1. And it's going to be 20. Oh, let's assume, I didn't write it down. Let's assume the pipeline is carrying the fluid at 20 degrees C, and the surface temperature is minus 10 degrees C. So it's a cold winter. So it's going to be 20 minus 10. If you do the math, Q is going to be 18.3 times 10 to the power of 6 watt. Or going to be 18.3 megawatt. Okay? Or 18.3 megajoule per second. This is the rate that we are losing heat through this 100 kilometers of pipeline. Now from table 4.1, we also see that if Z is less than 3D divided by 2, if Z is greater than 3D divided by 2, Z is 2, and 3D, D is 1 divided by 2, which is greater than that, then we can use this relationship. S is going to be 2 divided by natural log of 4Z divided by D. If we do that, Q would be 2 watt per meter Kelvin, 2 times pi times 100, 10 to the power 3 meter, natural log of 4 times 2 divided by 1, 20 minus 10, and this will give you 18.1 10 to the power 6 watt. So there is a small differences from 18.3 to 18.1 megawatt. Now, if you were asked to find heat loss per unit length of pipeline, then that would be Q over L, which is for this case is going to be 18.3 times 10 to the power 6 divided by, it was 100 times 10 to the power 3. So it's going to be 183 watt per meter. So this is going to be the unit length of heat loss from this pipeline to the surface. Now, the problem, I just simplified that one. I made assumptions. Oh, there is another assumptions that I have made. The pipeline has a high thermal conductivity that I did not really mention here, so I didn't consider that. K of pipe is very high. Yeah. That everywhere here, like the thickness is very small, that I can assume the whole pipeline is at T1 temperature. Now I can release that assumptions, or I can make the problem a little bit more, I would say, realistic or more difficult, whatever you call it. I can have exactly the same problem. So I'm just gonna draw a schematic of what we can do. Let's say this is the surface that we have, and let's say we have a pipeline that transmitting oil, and this pipeline now has an insulation. So let's say this is insulation layer that we have. So let's say we have oil at 120 degrees C that we are just transmitting when it's buried, let's say 1.5 meters underground. And if let's say the diameter of pipe is 50 centimeter and the diameter with insulation, let's say is 70 centimeters, so it's 10 centimeters of insulations around the pipeline that happens. Then what we will have here, if you consider this S1 over Ks as a R of T conduction for the 2D part that we have, and if I draw the analogy for the resistance and current here, so we have T of S, T of surface, so let's say this is T of S. Then what we will have is, I'm just going to call it R of soil here. So we have this R of soil, which is going to be acting like the 2D from the shape factor that we have. Then we are going to have R of insulator that we have. And then we can have this R of pipe. But if we assuming the K of pipe is high, this resistance wouldn't exist here. And then we can have, this is T of oil inside the pipe. And this can be the R convection inside the pipe. Convection, which is 1 over HA. Let's assume like this oil that is flowing inside this pipe, it's just having the conduction, the convection heat transfer coefficient of H inside that. So I can have 1 over H, and I can have the R of pipe, but let's assume pipe is uniform. So here we are going to have T of oil outside or just at the line of the pipeline, and then we are going to have the T of insulations and R of insulation and then R of soil. And we can do the calculations similar to what we have done in previous chapter. So Q at the end would be delta T, the temperature difference, divided by sigma RT. So this R convection could just not exist too. Let's say if the H is so high, then this value almost would be like 0. So there would be no resistance against flow from the liquid to the point that the insulator is starting. So here, let's say this is the insulator. That's the part that we have R of ins for the insulator. And here is the solid all over around this pipe that we have this R of soil that we have defined here.